And Ennan, Jiaqi, and you guys might want to. Do you mind turn on your camera first? I'm gonna just take a screenshot and just to keep a record.
Yeah,
Okay.
I just turn on my camera. Yeah, can you see me?
Cool. Yeah, I can see everyone. Wonderful. I'll just
because I
take
have I was planning to go to bed after this talk.
Sure. Okay, I think let's see what we have.
Yeah, I'm here.
Right. Okay. Yeah. Okay. Cool. I think we pretty much got everyone here. The presenter, the guest of honor, and the students and the people are still joining. But I think we can get started. So before the presentation start, I will just follow the tradition. I'll just say a few words about the paper. Usually it's me or Matt. We take turns. Since he's not here today, I'll just briefly introduce this paper. So in the previous 4 meetings, I think we focus a lot of on wide area network and the host network, in particular PCIe and memory and cache controller, basically with the network within the host. We look at the wide area network like BGP and how Google use design this decentralized SDN and so on. And also how to verify them, like using Espresso, right? The paper from Qian University about how to reasoning about external routes. But in our previous meetings, we left out one very important, probably one of the most important type of network, essentially data center network, in particular data center networks equipped with GPUs, right? Essentially because all these deep learning jobs and in particular large language models and so on, they consume lots of resources in data centers and clusters. And how to orchestrate such resources, in particular from the both the computing side and the communication side, that's a very important issue. So today we are going to take this opportunity to look into this particular topic, and by reading the paper called Crux, Maximizing GPU Utilization in Deep Learning Training Clusters, the honorable mention award at this year's SIGCOMM. So, and our presenter would be Aranya Saha, a first-year undergraduate student from Bangladesh. So, and Aranya actually was one of the founders of this SIGCOMM Paper Reading Group. Aranya and approach Matt Sessers about how to want to run this reading group, and I'm just here to help make sure things happen. So. And also, we're honored to invite the 3 authors of this paper, Yu Guan, Jiaqi and Ennan Zhai. They are all from Alibaba Cloud. So so our schedule is like this, right? So Aranya, I'll turn the floor to you. You will make do the presentation in about like using about 30 or 35 minutes, and after that, we will the authors will join us for discussion and the Q&A from the audience. Sounds good?
Yeah, sure.
Okay, cool. Now the floor is all yours, Aranya. Thanks.
Thank you, Professor. So hello everyone, my name is Aranya Saha, and today I'll be presenting this interesting paper, and its title is Crux Maximizing GPU Utilization Deep Learning Training Clusters. So let me go to the first slide. I think the slide is visible, right?
Yes, they're visible. Yes.
Yeah. Thank you for the confirmation. So deep learning has revolutionized various fields like healthcare, finance, and autonomous vehicles recently. So, but there is a problem in deep learning, training. Like it comes with a very huge computational cost, and training deep learning models such as like there are big models like GPT-4 and other LLMs also, and vision transformers. They require clusters of thousands of GPUs. So to scale these models, workloads are distributed across GPUs, and it enables parallelism. And however, this distribution introduces frequent synchronization, demands. So GPUs exchange parameters, gradients, optimizers constantly, and this leads to significant communication overhead. So the combined computational and communication demands make DLT very highly resource intensive, and it requires efficient management of utilizing these GPU resources. So like so first we want to tell something about I want to tell something about what is multi-tenant DLT clusters. So why this is called multi-tenant? Because many DLT jobs, like deep learning training jobs, are many deep learning training jobs are done like are are distributed among same GPUs. That's why it's called a multi-tenant DLT clusters. And the components of DLT clusters are storage, hosts, and networks. The entire system is carefully designed to optimize data flow, minimize communication bottlenecks, and maximize the utilization of the expensive GPU resources. Here is a picture of the allocation of GPUs on DLT jobs. Here we can see that job 1 is done at the same time on multiple GPUs, and job 3 also is distributed among 2 GPUs at the same time. So what is the main problem in DLT clusters? The main problem in DLT clusters is actually the communication contention. It is one of the biggest challenges in multi-tenant clusters in DLT training tasks. So imagine multiple deep learning jobs sharing the same network infrastructure. These jobs generate traffic that needs to be distributed efficiently across network paths. So ECMP is a common routing mechanism, and it hashes traffic flows to paths. But when flows are hashed to the same path, congestion happens, congestion occurs. So for example, we have observed a real world scenario that was on the paper, and it was like running a 64 GPU GPT variant job alongside a 16 GPU BERT job on the same cluster. It actually results in a drop of 9.5% decrease in GPU utilization. And if we compare it to running the GPT job alone, so uh, we can so this single scenario explains uh, like what is the main problem behind running 2 jobs on the same cluster. So the communication contention in this scenario led to an 11% increase in GPT job inference time, reducing the throughput by almost 10%. These findings underscores the urgent need for communication schedulers like Crux, which can intelligently manage data flow and mitigate contention and maximize the efficiency in DLT clusters. So there was another study at Alibaba Cloud, which was also on the paper, and it was 36.3% of jobs were at risk of communication contention, and 51% of GPUs were affected. So we can very well understand the importance of addressing the communication contention in DLT clusters. So there are some pictures of how communication contention can occur. Like in figure 3, we can see that there are 2 jobs which are sharing one route or path, which can lead to contention in this case. And here we can see that GPT and BERT are sharing one common path, and for which there is a big contention. So there are 2 types of scheduler actually, and one type of scheduler is job scheduler, and another type of scheduler is communication scheduler. We are working with the communication scheduler in this paper, and Crux is one kind of communication scheduler that that targets the communication contentions in DLT training tasks. So here is a picture which is depicting.
Hello? Can other people hear, or is it just me?
Are waiting, and if we assign the high priority to job 2, one GPU is waiting.
Aranya, sorry to interrupt. But can you repeat this example? I think maybe your network just dropped a little bit, so people couldn't hear the example clearly. Can you just repeat this slide? Yes.
This slide, example of why
Yeah.
optimizing. Yeah. Okay. Thank you.
Yeah.
So
Sure.
in figure A, we can see that if job one uses one GPU and job 2 sorry so I'm really sorry. So in figure A, we can see that if we assign higher priority to job 1, 10 GPUs are waiting, and if we assign higher priority to job 2, 1 GPU is waiting. So we have to decide when we have to assign high priority to which job. This is very important in this kind of tasks. So what is Crux actually? So Crux is our solution to communication contention. It's a communication scheduler designed for multi-tenant DLT clusters. Its primary goal is to maximize the GPU utilization by optimizing data flow among DLT jobs. And Crux achieves this by 3 types of steps. The first steps is uh, prioritizing larger jobs, and the second step I would say is prioritizing job with more computation, and the third step was prioritizing job with less communication. Now we have to, I think there is something to tell about these 3 steps. So what is actually prioritizing larger jobs? Let's say we have like 3 or 4 jobs or whatever, multiple jobs. And if we prioritize larger jobs, then the GPUs are uh, like busy for a longer time. So the utilization of GPU is much better if we prioritize the larger jobs. This is the first insight. The second insight was prioritizing job with more computation. So if we don't do that, then GPU will sit idle for more time, which will make our profit lesser, or which will make huge loss. And the third insight was prioritizing job with less communication. If the communication is less, then we can use the GPU more for computational purposes, which will actually benefit our like profit or something like that. So what is the key methodology behind Crux? Uh, what the concept of GPU intensity? So what is GPU intensity? GPU intensity is actually the ratio of computation workload and maximum time required. Jobs with high intensity indicates that it can perform a substantial amount of computation relative to the time spent for communication. So if we prioritize jobs with higher GPU intensity, it means that it will actually maximize the overall GPU utilization. And Crux leverages the concept of this GPU intensity in its path selection and priority assignment algorithms. It aims to select paths that minimize contention for high intensity jobs and assign priority to ensure that this job's communication is not delayed. So GPU, so now what is GPU intensity based path selection? So Crux first like methodology was GPU intensity based path selection. So GPU intensity based path selection, there are some traditional routing methods like ECMP, and but these type of routing techniques have limitations. They distribute traffic based on uh, simple hashes, which often fail under the sparsity iterative communication patterns of deep learning. So Crux addresses these limitations by prioritizing based on GPU intensity selecting the least congested path, and also dynamically adjusting path assignments as the cluster environment changes. So this dynamic GPU aware approach ensures balanced utilization across paths and prevents bottlenecks even as jobs start and finish. So the next methodology that Crux follows is priority assignment. So, what is actual priority assignment? Scheduling becomes more nuanced when considering job characteristics like iteration length and computation communication overlap. For example, a job with shorter iterations may require higher priority to avoid idle GPUs. Jobs sensitive to communication delays must be also prioritized. So Crux balances these considerations using a correlation factor that adjusts priorities dynamically, ensuring the optimal balance between network utilization and GPU performance. Uh, so next idea that Crux follows is priority compression. This actually, hardware limitations of the problem is actually uh, if we have many GPU if you have many GPU intensive jobs, then and sometimes it can happen that we don't have that much GPU available. So in that time, we can actually compress many unique job priorities into fewer levels. And it actually generates a topological orders of DHG using breadth first search, which is a common, and it computes the maximum K cut using dynamic programming, and then it selects the best K cut with highest total edge weight. So what is the outcome of this compression? It actually
Recording in progress.
It actually reduces the negative impact of compression and improves the overall GPU utilization by minimizing communication contention. Here is the more description, more destructive, more description of priority compression algorithm, and the outcome is actually the same as mentioned in the previous slide. It reduces performance loss from priority compression and ensures jobs with high contention are separated, improving overall GPU utilization. So what is the effectiveness validation micro benchmarking? So there was a there has been a simulation set up to measure the performance of Crux and compare it with other baseline scheduling methods, communication scheduling methods like TACCL, Synchronia, and Verise. And interestingly, Crux has outperformed almost all of the baseline methods of uh, communication schedulers. The results actually the results are very impressive. In path selection method, Crux intensity-based path selection algorithm demonstrated a remarkable almost 97.69% performance level compared to the optimal solution. In priority assignment, the percentage was 97.24%. In priority compression, the achievement was 97.12% of the optimal performance. Overall, the micro benchmark simulations provide strong evidence for the effectiveness of each component of Crux design. There are actually two core modules of Crux, Crux daemon and Crux transport. So Crux daemon is actually it collects information and makes communication scheduling decisions, and Crux transport executes those scheduling decisions. Here are the implementation details. So Crux optimizes communication scheduling in GPU's clusters without modifying DLT model codes. It does this in three steps, I would say. The first is path information probing. Hosts it GPs source ports using ECMP and INT of data communication overs via hardware monitoring and decisions on job completion.
Hi, Aranya. I think the network is still spotty. So maybe to save the bandwidth, maybe you could turn off your camera. I think that might make sense. Aranya, maybe turn off the camera, not to stop the sharing. You can still share the screen. You need to turn off your camera, your video. Hello?
Hello, I think my network was unstable. I'm sorry for that.
It's all right. You can still share your screen. Yeah, we can see the screen. Yes.
I think I was here, or maybe in this slide, right?
Yeah, I
Professor?
believe so. Yes. Yes, I believe so. Yes. Yeah.
So I was talking about the implementation details. So Crux app optimizes communication scheduling in GPU's clusters without modifying the deep learning training model codes. So it for path information probing, there are two types of path information, intrahost and interhost, and it uses various types of tools for intrahost and interhost path information probings. And for job information measurement, it measures computation and communication overloads via hardware monitoring like GPU, NIC, and PCIe. And for scheduling decisions it can happen on job arrival or completion. Crux reassigns paths and priorities. So for path selection, in the case of path selection for inter-host communication, ECMP and ROCEV2 are used, and intra-host communication uses the nearest NIC or NVL link. For priority assignment, sets traffic classes for inter-host networks and uses semaphores to manage PCI access for intra-host communication. So yeah. So let's go to the evaluation of real-world test bed. So a 96 GPU test bed was used for this real-world evaluation, which is composed of 8 aggregation switches. They are further connected to 6 TOR switches, which is connected to again 12 hosts, and each of the hosts includes 800 GPUs, which are interconnected through a 2-layer closed network. And evaluation was done on 3 models: ResNet, BERT, and GPT. And ResNet is comparatively a small size model, and BERT and GPT are large models, language models. So here you can see that if we use Crux, our overall, if we use Crux, our overall performance increases. Then if we don't use Crux, our performance drops. In this slide, we can see that. And in every cases, Crux made better utilizations. Here we can also see that without Crux, the performance was less, and after using Crux, it was almost equal to the ideal GPU utilization. And in the case of in the case of time, BART and GPT, when we evaluated it on BART and GPT, the time reduced to 15% and 18%. But in the case of ResNet, it did not, reduced. But overall, we can say that our like Crux outperformed other non-Crux methods, I would say. Okay. So another type of evaluation was done, and that is trace-based simulation. It's a kind of like simulation-based evaluation, and we compared Crux with other baseline methods like Synchronia, TACCL, and Cassini. And Crux configuration was 3 types. First, we took priority assignment, then path selection with priority assignment, and then all 3 methods: priority assignment, path selection, and priority compression. So simulation, here the simulation results, we can see that in clause topology, 13% to 23% improvement was seen in GPU utilization versus other baseline methods. And in the case of double-sided topology, the improvement was 4%, from 4% to 7% in GPU utilization. So we can say that Crux effectively mitigates the communication contention and optimizes GPU utilization. And it prioritizes GPU intensive jobs and efficiently utilizes network resources for better overall GPU performance. We can visualize the overall Crux impact. So here are some graphs which tells. So the color gradients, darker colors in this picture, the darker colors are actually higher GPU intensive job data flow. So in the case of Synchronia versus Crux PA, we can say that in Synchronia, we can see that darker colors are less than using Crux PA here. So it is very evident that Crux PA, Crux path selection algorithm, priority assignment algorithm has improved in GPU intensity distribution. And in the case of PSPA and full, also this is very much evident. So key findings from the comparisons are Crux PA improves GPU utilization 26% more than Synchronia, 14% more than TACCL, and 5% more than Cassini. And in other methods also, we can see increase in performance, which actually results in efficient network resource usage and improved GPU utilization and increased high intensity traffic. So Crux and job schedulers. So in the first, we have said that there are 2 types of schedulers, job schedulers and communication schedulers. Crux falls under the category of communication schedulers. So Crux and job schedulers can work actually together. And actually, job schedulers focus on high-level job and high-level job arrangement, but Crux optimizes communication scheduling within those arrangements. So we have to use actually both of these to get better results. And evaluated job schedulers are HiveD and Muri. So we can see the performance results, GPU utilization improvements. HiveD alone does 25% and Muri alone does 20%. But if you use Crux with them, improvement is done further 11 and 14%. And the the insight is even with advanced job schedulers, communication contention remains, and Crux mitigate this very effectively. So here is the conclusion and future work. So what are the Crux contributions? So the primary contributions of Crux is basically GPU intensity. It introduced a metric for optimizing communication scheduling. It introduced some novel techniques like path selection, priority assignment, priority compression to maximize GPU utilization. Performance improvements. It achieved significant gains in both real world and simulated environments. So what can be the future work? In future, maybe the focus can be done on refining Crux algorithm and exploring fairness considerations in scheduling. Maybe, we don't know. Okay, so thank you. This was my presentation. I know maybe I have made some mistakes and I apologize for that. I have tried my best. So I rest my case here.
Can you share the slides?
Sorry?
Can you share the slides?
Yeah, sure. I'm
You can put them in maybe in a Google Drive or something and send us a link.
right. So, okay.
Maybe
So,
I'm putting
Right.
I'm
So-
put it in the chat. Put it in the chat.
Yeah, so Hasham, right? I don't know if I pronounced your name correctly.
Yes,
So
yes.
yeah, so what we do here is we video record all our meetings, and we will later post the meeting on YouTube and also other video websites. And in terms of slides, we currently didn't. That's a very good idea. We didn't collect all the slides of previous meetings, but we can do that, and we will post it on a Discord site called Everything in SIGCOMM. We will post all the slides over there. Does that sound
That will
okay
be
to you?
that will be great.
Okay, wonderful.
Yeah. Can you show me the initial slide? I missed it. Where you define Crux? You had a slide, and I joined later, so I missed the slide, the introductory slide, which should talk about what Crux is. Maybe if you can share it, show us the
Yeah,
slide. This one slide.
Yeah, Aranya, you can still share your screen. You can still share your screen.
I guess
think.
I guess we should share the slides to our audience. So because we can talk about based on it.
Yeah, definitely. Yeah. So, which maybe slide number 5 or slide number 6?
Yeah, maybe when you define Crux, I came up.
this slide?
Yeah, I think I came to this slide, but maybe is this where you define what Crux is?
So what Crux is actually?
Yeah, number 9. Then I think that's actually
So you
slide
say
number
Crux.
9.
Right.
Yeah, exactly. That's it. Thank you. Thank you very much.
Yeah, so actually regarding to this slide, I think it's very important, and Crux, the goal for Crux is to maximize GPU utilization, right? I think as a cloud provider, that's Alibaba has every reason to do so. But in the meantime, I'm curious, like because if I'm a client, I rent GPUs from Ali Cloud, and I pay by the hour, right? So,
Yeah.
but if my training job my job completion time is prolonged, does that mean I have to pay more? And so what's is it possible to review the number in production networks, like or what's the rationale behind that? Like how much the client has to pay how much extra the client has to pay for that.
Yeah.
So Ennan or Jiaqi or you do you have some thoughts on that?
Okay. Thanks for your question. I think there are 2 points. The first point is in our experience, usually a model with high GPU intensity, the cluster usually pay more because it includes maybe thousands of GPUs. So you can let me think. You can understand. You can regard our goal of maximizing GPU utilization as maximizing the weighted average of all deep learning training jobs in our cluster.
Mm-hmm.
And the weight is the number of GPUs or something like GPU intensity. And the second point is if you want to make the fairness, you can just make let me think, make a weighted average of GPU intensity and something like fairness factor that can improve the fairness problem.
Yeah, but wouldn't that because I see I saw in the paper that essentially you did this very nice analysis about how to maximize GPU utilization essentially by following the some basic scheduling principles. You can approach like 100% GPU intensity, but if you change your objective function to include a weighted factor, for example, job completion time or fairness, would that essentially would your theorem, for example, theorem 1 still hold? Would that break your analysis result? Have you tried that before?
Yes, that will break the theorem in the paper.
Right.
Let me give another angle.
Yeah.
So maximizing the GPU utilization on the other hand is kind of like reducing the per GPU cost. So I indeed like what you said, like we are going to prolong the jobs for like that use fewer GPU, right? But sorry, but on the other side, if we can increase our GPU utilization, then in a specific cluster at given scale, then I think on the other hand, we can reduce our price for smaller jobs, right? So if you wanna, then on the other side, you can either pay less for a little bit longer time, or you can improve your efficiency by a little bit increasing your cluster scale, right? So that kind of like that is also based on our equation. You are increasing your weight, and that means you will have statistically you will have higher weight, and you will have higher priority in your network, which means your job will run faster than the non-Crux version, right? So I think it's more like indeed, yes, given the same money, if I'm using Crux, then probably my job is going to run longer. But in the other, what I want to say is using Crux, then we can reduce our charging for all the customers, given that the entire GPU has a high GPU utilization, which means we are wasting less money. And that means that goes to we can give more profit to the users. But I think, unfortunately, we don't have a detailed number to quantify that because it's more like a statistical thing. But I think this is how the logic would go.
I see. Yeah, that makes sense. I think. Yeah, yeah. In general, I think that makes sense. And I mean, you essentially run your GPU resources, and I think that at least from the experiment, either from using trace-based simulation or testbed experiment, I think the increase of job completion time is very minor, right? So it's not even in that means in this case, even if we maximize, we choose to maximize GPU utilization in terms of job completion time, it's more like a side effect is that we do not sacrifice job completion time too much, right?
Yes, and because we have path selection to try our best to avoid communication contention between jobs. Yeah,
I see. Yeah. So I actually I think this is a very nice scheduling paper, but I think I asked this question on behalf of many researchers or students here or in your community. Like scheduling is a very classic and well-studied topic, right? And in your related work, in your introduction, you mentioned that in the previous decade, like there are so many scheduling papers, right? And not letting alone there are even more before that, right? So like the series of all kinds of co-flow scheduling papers appeared in SIGCOMM, SIGCOMM, and even InfoComm and ICDCS and etc. And so what essentially makes Crux unique? Is it because you pick GPU utilization as the objective function that making this problem unique, or is it like you considered other factors in the scheduling that make this problem unique? And by making and what is the fundamental challenge in solving this problem?
I think for your first question, what makes Crux unique? I think is the optimization goal of maximizing GPU utilization makes the strategy of communication scheduling different from the previous works. That is the.
I think maybe we can move the slides to page 7.
Aranya, can you move the slides to page 7?
Yeah. Anya or Aaron, yeah, could you please, yeah. So yeah, I guess you can answer the Charles' question based on the figure 2, I think, because yeah, we put a lot of efforts on making this picture, right?
Yeah, my point is that the goal of optimization of GPU utilization makes the strategy of previous work no longer optimized. So we need a new theorem and new algorithms to approach the to approach our goal with new algorithms. Yeah.
I see. So I see. I probably this just my understanding is essentially is maximizing GPU intensity. That's that hasn't been looked into, and how to achieve this goal by scheduling the network communication of different jobs. I think that probably is something that because if you want to when people think about how to maximize like a CPU utilization or VM server utilizations, that somehow falls into the category of job scheduling. But here in Crux, you guys try to maximize a similar goal, but by considering communication, because in deep learning training jobs, communication is one of the most one of these key bottlenecks, right? I think that would make this thing make this paper unique and standing out. That's my understanding.
Yeah.
Can you go to slide number 10? Number 10. Yeah. So how we can do the scheduling across multiple data centers, which might be located in different places?
You mean
You can have, like if you can do the training using multiple data centers, maybe one in New Jersey, one in Santa Clara,
Right.
they are distant apart.
So I guess the Crux doesn't target this scenario.
I think currently Crux doesn't target on optimization, communication, scheduling for jobs in different clusters because usually I think usually they are.
So currently you only focus on one data center, right?
Yeah.
Yes.
We focus on jobs in one data center.
Yeah. So the picture in this slide is one data center.
Yeah.
Got it. And you are using spine and leaf, right? Architecture.
Pardon?
You are using
spanning and leaf. Yes.
Okay,
Yes.
So the focus or the scope of this paper is one data center with the spine and leaf architecture.
Yeah.
Okay, got it. That explains it.
That's a standard factory architecture, cloud architecture. Yes.
Exactly. Thank you for the clarification.
Yeah.
So related to sorry, Ennan, you were saying?
No, I just want to put some complementary thing to some question, because so far in our business we mainly focus on just within one single data center to schedule the jobs or schedule the communication. We thought about whether in the future we may have the, say, job scheduling across data centers, but we haven't done so. Yeah, but I think that's a very interesting future direction the researchers can think about, because we haven't done a real job scheduling across the data centers, because the business and the services now do not quite necessarily need that. But I guess in the future we may have, say, a super big large language model training jobs. We need to train multi jobs, say, or the entire job across the data centers. But I guess this is a very interesting direction. I just to put some complementary notes here.
Yeah. Have you heard of the UA Link consortium?
That's I guess that's another story, right? UA Link, I think Jiaqi, I think you are very familiar with UA Link, right? Is that my correct? UA Link is the inter GPU connection,
it is
right?
the ultra accelerator link consortium.
Yeah. But my understanding is that's mainly focused on the inter GPU, right, within the single rack. Is that true?
Actually, I have to admit I haven't looked at it in details. All I can tell you is that Alibaba is not in this consortium so far.
Alibaba is in. Actually, if you look the UA Link website.
Really?
Yes.
Okay, good.
Yes.
Good.
I think we're both, right?
Because when I looked at their papers, they said they have AMD, Astera Labs, AWS, Cisco, Google, HPE, Intel, Meta, and Microsoft, but not Alibaba. But if Alibaba is there, that's great.
Yeah, there are a lot more than that, but yes, indeed, Alibaba is there. Yes. Yeah, this is a large consortium. Yeah.
Exactly. And I'm sure you are considering it in your future research, or it will be current research.
Right. But Jiaqi, I guess, and Hassan, I guess maybe the UA Link thing is kind of different from the job scheduler.
I know. Yeah.
Okay. I just want to confirm. Yeah. Okay. Great. Yeah.
I got it. Yeah. I got it. I just want to find out. And you already corrected my understanding. Alibaba's there. That's all I think I need to know.
Right. Yeah. I think that's another great. Yeah. Okay. Anyway. I think just the final sentence. I guess that's another interesting direction. For the scale up network, right? I guess this afternoon I just also talked with Jiaqi about this. But anyway, yeah. I just.
Is any one of the authors or the presenter in Santa Clara? If so, we can meet.
I guess none of us do that.
I don't.
But Jiaqi, are you familiar with any of us or any members in our team will do that? I don't know. I guess
No,
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 right?
no. I think no
Okay.
in Santa Clara, not in
Okay.
only in the
Okay,
Bay Area,
okay,
right? Yeah.
Okay,
okay, okay.
Jiaqi is our leader member for the UEC and the UA Link stuff, and he organized and tried to join the the meeting to do the presentation, but I guess maybe not Santa Barbara this year.
Okay, it's a great work. Thank you very much.
Thanks.
So following on our other questions, I see Wenqi Luo post a question in the chat. So first he compliment this is a very outstanding paper, and his question is regarding the problem formulation in section 3.1 of this paper. Because in 3.1 you model the GPU cluster as a graph, right? With where nodes are essentially the GPU nodes. Nodes in this graph are essentially GPU nodes, and the links are links connecting these GPU nodes. So he's wondering, since this graph does not has any switch, so how do you capture the GPU class topology and the potential communication contention?
Sorry, can you repeat the problem?
Yeah. So in paper section 3.1, you model GPU cluster as a graph, and in this graph, the nodes essentially are GPU nodes, and the links are between the links are essentially between connecting different GPU nodes. So Wenqi's question is, since this graph does not have any switches, so how do you capture GPU's topology or potential communication contention in this GPU cluster in this formulation?
Because generally, when two DLT jobs has communication contention, their performance is totally decided by the most bottleneck link. So we only need to consider one link rather than all links. Yeah.
So essentially, oh, I see. So essentially, I don't know if I interpret that correctly, but essentially, because you only consider the bottleneck, and this bottleneck does not have to have a switch. Essentially, this graph is more like an abstract graph. You do not have all the links in the topology considered. You only consider the bottleneck, and you abstract this bottleneck as a link connecting two GPUs, something like that.
Yeah.
Is that correct?
Yes. When there are two jobs, maybe there are multiple links. There are communication contention on multiple links, but we only need to consider the most congested links, because only these links decide the two jobs' performance, and other links that is not it's not the bottleneck of the whole performance of the GPU cluster. Yeah.
I see. Yeah, I think that should answer Wenqi's question, right? So, yeah, I see Wenqi got it. Yeah, great. So, I have another question regarding like what could be the next for this work. So, in your category of related work, you mentioned that there are two types of scheduler: job scheduler and communication scheduler. So, I would think a very natural question would be, what if we do like a joint scheduling of job and communication? So have you guys look into that, or you think that's we don't have you don't have to do that, or you think that maybe that's too complex, or so you leave it for future work? So what's your take on this?
Okay. First,
I guess we just I guess we just put the job scheduler and the communication scheduler together, right? Which means we just first run the job scheduler to put the job across machines, and then run the communication scheduler. Do you think that's a correct sequence to run the two types of approaches?
Yes. So his question is it worth to do a joint optimization of job scheduler and communication scheduler? I think there is a saying that let's pay most of the gain. Yeah, for a system designer, if a simple design can work well, we don't need a complex design. But I'm not sure. Is there a significant potential improvement if we do a joint optimization of job scheduler and communication scheduler? I just am not sure the number of the improvement. So we can leave it to our future work. Yeah.
Right, I see. Yeah, I agree with you. Something because you have something, you already have some simple, you already get most of the gain, right? So you might not worth the time and efforts, engineering efforts to work on a more theoretically more appealing, but in the end, you may not get enough benefits back, right? I totally agree with that.
Yeah.
But my intuition,
my intuition.
yeah, of course, I agree. My other intuition regarding this would be in data center, like we have this very sort of like very symmetric and fully richly connected topology, doing joint optimization of job and communication might not give you enough gain, because we indeed the data center has a lot of links. It's a very richly connected network, but in wide area that might be different. Doing like a job routing and scheduling joint optimization in wide area networks, because wide area networks usually typically has a asymmetric and very irregular topology. I think that might actually make more sense to do routing and scheduling joint optimization. That's my intuition, but of course I don't have a good data for that either.
I think that should be put in. Yeah, go ahead. Yeah.
Right. So we have two more questions. I know we only have 3 minutes, but we have 2 more questions from the audience. So Ning Xu asked his question is, model training is essentially an iterative process with computing and the communications. So will Crux with highest GPU intensity waste some network resources when this higher GPU intensity job is computing? It's in the chat. Yeah.
What's the meaning of waste the network communication?
I guess it's just the fairness problem, right?
Yeah, I would think so. Yeah. So essentially, if you but essentially, I think that yeah, I think that's that may not be an issue, right? Because one GPU with highest intensity essentially is computing. You do not communicate, right? So when you do not communicate, we can just allocate resources or allocate resources to other jobs who needs to communicate, right? So that's
I cannot remember. I cannot remember the details. So yeah, I guess we answered this question in our appendix or camera ready. I cannot remember the details about this. The fairness problem.
I think it's in one of the discussion sessions you talk about the fairness. Yeah.
So can I just repeat the question?
You're talking about chat.
The network.
You can click the chat room. Yeah.
Or something like that. I think the target of GPU cluster is do more computation and more computation. So if scheduling decisions can optimize the GPU computation, we do not need to care whether the network communication is they are waste of network or something like that, because our goal is to do computation. Yeah.
Right. So one more question. I think that that's from Xuan Hao. Actually, I think Xuan Hao is from my group. So his question is that because scheduling policy is determined based on GPU intensity, so would this lead to the problem of starvation? For example, for tasks with lower GPU intensity, would those tasks essentially will always be preempted by new coming high intensity jobs? So eventually they couldn't get enough network resources to transmit. Would that could that happen, and would that happen in reality?
Okay, I got the question. So actually, we did some experiment about that, about whether low GPU intensity jobs will be will be significantly slower than running along. First, in state-of-the-art deep learning training jobs, there are a lot of bubbles between each communication. Right. So it always have even a low GPU intensity job is always have chance to communication for data transferation. Yeah.
Right. But follow up that for what if, that's what if, because there are also ML system work talking about we use this pipelining, right? So we compute a small batch and then we just communicate. So essentially for single job, we can hide, we do not separate communication and the computation. We just merge them, we just pipeline them. So basically we can hide a large portion of communication during the computation. So essentially, imagine two rectangular. We can put two rectangulars in parallel, but zigzag way. So that essentially for a single job, that means while I'm computing, some intermediate result of my computation can be transmitted. So that would mean this job essentially would utilize all the communication resources it can get from the network. So if the machine learning system itself is designed in that way, doesn't that mean Crux, there is a higher chance for Crux to starve jobs with low GPU intensity? Is that right?
You mean when the computation and communication have a lot of overlap?
Overlap for single job. They overlap because I read several papers talking about how to overlap the communication and the computation so that the total length of the time can be shortened, right? There are several papers proposing those similar designs.
Yes. For state-of-the-art deep learning training jobs, most computation can be overlapped by computation. Yes, but I think 2 points. First, there are still some collective communication become the bottleneck of the whole training jobs. And my second point is even some communication can be overlapped by the computation. Based on our experience, for most training jobs, the most time is spent on GPU computation. Yeah. So back to my previous point, there are always bubbles between multiple GPU computation kernels.
Yeah. So I guess my question would be, yeah, I like the analogy of bubbles. My question really is, other machine learning systems focusing on a single job, they're also trying to squeeze in all those bubbles.
Yeah.
So if there's a machine learning system if there's a system for every single job, it squeeze as much bubble as possible out. of this single jobs training process.
Yeah.
That means for each job itself, it doesn't. For each job itself, it does not have much bubble left. So
yeah. So
in that way, it would give the we would have the appearance that this job is utilizing communication, computation resources and the network resources at the same time. So that, and then if there's another job with low computation intensity, because there's no bubble left for these high intensity jobs, that means it has lower, in that case, it could starve this low intensity job, right? Because it couldn't get enough network resources.
Oh, okay, I got your question. The fact is that when I say bubble, I mean a bubble between GPU computation kernels. Yeah. Suppose you can suppose one can do his best to overlap. Let's say overlap 100% of communication with computation. Yeah, but there are still bubbles between communication. Maybe now there are no bubbles between computation kernels, but there are always bubbles between communication because, for example, for deep learning training jobs, in one iteration it needs 5 seconds for computation, but maybe it only needs 2 seconds for communication. Even all communication can be overlapped by computation. There are still 3 seconds left. Did I answer your question?
Yeah, I think I get your idea. Yeah, let me think about that more. Since I have your WeChat, I can find you to discuss more that in more details later. Yeah, I think, but I think I get the gist. Yes. Okay, so I think unfortunately we are already 7 minutes over. I think this paper draws a lot of questions and discussion. I think it's a very nice presentation from Aranya. I have to say, for undergraduate student, you did a fantastic job. Yeah, and it's for all the audience here, if you haven't read the paper, I strongly recommend you reading it during your Christmas break. And since this is Christmas and New Year's break, so our SIGCOMM Paper Reading Group will recess for a couple of weeks. And our tentative schedule would be, we will resume our paper reading on January 15th. So please stay tuned for future announcements. And again, thanks Aranya for the presentation, and thanks thank you, Jiaqi and Ennan for the discussion. Yes, it's a really very insightful discussion. Thank you, everyone.
Thank you.
Thank you.
Bye bye. Good night.
All right. Thank you.
Bye.
Bye. Have a good day and good night. Thank you. Bye.
Thank you.